In this presentation, we'll examine the behavior of sequential circuits. We determine the behavior of the sequential circuits from the input, output, and present state of the circuit. The outputs in the next state are a function of the inputs in the present state. The analysis of a sequential circuit consists of obtaining a suitable description that demonstrates the time sequence of inputs, outputs, and states. You'll recall that a logic diagram is recognized as a synchronous sequential circuit if it includes flip-flops with clock inputs driven directly or indirectly by a clock signal, and if the direct sets and resets are unused during the normal functioning of the circuit. We'll discuss algebraic representations, state tables, and diagrams in this presentation. The logic diagram of a sequential circuit consists of flip-flops and usually combinational gates. The type of flip-flops used in a list of Boolean functions for the combinational circuit provide all the information needed to draw the logic diagram of the sequential circuit. We need to pay special attention to the part of the combinational circuit that generates the signals for the inputs of the flip-flops. These can be described by flip-flop input equations. A flip-flop input equation is a Boolean expression for a combinational circuit. The output of the combinational circuit is connected to the input for the flip-flop. Flip-flop input equations imply the type of flip-flop from the letter symbol, and they fully specify the combinational circuit that drives the flip-flop. Here's an example of a sequential circuit along with its equations. The first two equations are for the flip-flops, and the third gives the output y. The subscripts designate the outputs of the respective flip-flops. The functional relationships among the inputs, outputs, and flip-flop states of a sequential circuit can be enumerated in what is called a state table. The state table has four sections: present state, input, next state, and the output. The present state section shows the states of the flip-flops A and B at any given time t. The input section gives each value of x for each possible present state. Note that for each possible input combination, each of the present states is repeated. The next state section shows the states of the flip-flops one clock period later at time t plus 1. The output section gives the value of the output y at time t for each combination of present state and input. The derivation of a state table consists of first listing all possible binary combinations of present state and inputs. The next state values are then determined from the logic diagram or from the flip-flop input. The state table for any sequential circuit with D flip-flops is obtained in this way. In general, a sequential circuit with M flip-flops and N inputs needs 2 to the M plus N rows in the state table. The next state section has M columns, one for each flip-flop. The binary values of the next state are derived directly from the D flip-flop input equations. The output section has as many columns as there are output variables. Its binary values are derived from the circuit or from the Boolean functions in the same manner as in the truth table. A two-dimensional state table having the present state tabulated in the left column and the inputs tabulated across the top row is also frequently used. The next state entries are made in each cell of the table for the present state and input combinations corresponding to the location of the cell. A similar two-dimensional table is used for the outputs if they depend on the inputs. Sequential circuits in which the outputs depend on the inputs as well as on the states are referred to as Mealy model circuits. If the outputs depend only on the states, then a one-dimensional column suffices. These are Moore model circuits. Each model is named after its originator. This is an example of a Moore model circuit. The state table has one column for the present state and one column for the inputs. The next state and output are also in single columns. Next state is derived from the flip-flop input equation, which specifies an odd function. The output column is simply a copy of the column for the present state variable A. The information available in the state table may be represented graphically in the form of a state diagram. A state is represented by a circle, and transitions between the states are indicated by direct lines connecting the circles. The state diagram for the sequential circuit we discussed earlier in the presentation is shown here. It provides the same information as the state table, but it's in an easier format for us to understand. The binary number inside each circle identifies the state of the flip-flops. For Mealy model circuits, the directed lines are labeled with two binary numbers separated by a slash. The input value during the present state precedes the slash. The value following the slash gives the output value during the present state with the input applied. For example, the directed line from state 00 to 01 is labeled 1/0, meaning that when the sequential circuit is in the present state of 00 and the input is 1, the output is 0. After the next clock transition, the circuit goes back to next state 01. Consider a logic diagram for this circuit. Here only one flip-flop with two states is needed. Here we have a Moore model circuit. The slash on the directed lines is not included since the outputs depend only on the state and not on the input values. The output is indicated inside the state circle, indicated with a slash. There are two input conditions for each state transition in the diagram separated by a comma. When there are two input variables, each state may end up having up to 4 directed lines coming out of the circle. So, which is better, state table or state diagrams? The state table is easier to derive from the given logic diagram and input equations. The state diagram gives a pictorial view of the state transitions, the form more suitable for human interpretation of the operation of the circuit. In terms of Mealy or Moore machines, it's also a matter of personal preference. It's also possible to mix Mealy and Moore type outputs, and the text is an example where this works. Two states are equivalent if the response for each possible input sequence is an identical output sequence. State reduction through state equivalence may or may not result in reduced cost, since the cost is dependent on the combinational circuit cost as well as the flip-flop cost. Nonetheless, combining equivalent states has inherited advantages in design, verification, and testing processes. Simulation of sequential circuits is different from their combinational counterparts for several reasons. First of all, rather than a set of input patterns for which the order of the application is immaterial, the patterns must be applied in a sequence. Second, there must be some means to place a circuit in a known state. Realistically, initialization to a known state is accomplished by an application of an initialization subsequence at the beginning of the simulation. In the simplest case, we can use the reset signal. Third, we need to observe the state to verify its correctness. In some circuits, application of an additional sequence of inputs is required to determine the state of the circuit at a given point in time. The simplest alternative is to set up the simulation so the state of the circuit can be observed directly. For example, we can add a circuit output with a path from each state variable signal. A final issue to be dealt with in more detail is the timing of application inputs and observation of outputs relative to the active clock edge. The objective of functional simulation is to determine or verification of the function of the circuit. In functional simulation, components of the circuit have no delay or a very small delay. Timing simulation is much more complex. Here the circuit elements have realistic delays, and verification of the proper operation of the circuit in terms of timing is the simulation objective. Having a very small component delay for functional simulation can create problems, particularly if the clock period is less than the longest delay in the circuit. In addition to the clock period, the time of application inputs relative to the positive clock edge is also important. The final issue is the time at which to examine a simulation result in functional simulation. At the very latest, the state variable values and output should be at their final values just before the positive clock edge. Although it may be possible to observe the values at other locations, this location provides a foolproof observation time for functional simulation. Thanks so much for watching, and don't forget